everyone, my name is Kristen Womble. I am a research associate at Tennessee Tech University working with the co-op unit, and today I'm presenting on a habitat suitability model that Dr. Amanda Rosenberger and I have built for the Tennessee Heelsplitter. So this is Lasmigona holstonia. It's a small-shelled anodontine mussel. Typically occurs in small to medium streams in sand, gravel, and mud substrates. Oftentimes it's found in mud banks along the stream margins, like the image here. And a lot of folks have also noticed that it seems to like the areas near spring upwellings. It's restricted to the Tennessee River and New River drainages in the southeast, and it also seems to more or less be restricted to the Ridge and Valley ecoregion. So in the Tennessee system, it goes down as far upstream as the Paint Rock River drainage. One thing that's interesting about this species is it tends to become locally abundant in small first and second order streams where it's the only bivalve mollusk present at all. And so this is an example of that. This is Reimer Branch in the Ocoee River drainage in southeast Tennessee. You can see it's a very small site, but this population seems to be doing really well. We have decent abundance, lots of size classes, evidence of recruitment. And so these species that seem to prefer first and second order streams can be difficult for us to study because historically our sampling in first and second order streams for freshwater mussels has not been as prominent as for larger streams. So these areas are underrepresented in our sampling. We don't have a lot of long-term mussel monitoring data for streams like this in general. And so this becomes an issue for species that become petitioned for listing or have some conservation need, like the Tennessee Heelsplitter, because these knowledge gaps can really inhibit conservation managers from being able to make fully informed decisions. And so that's kind of what motivated this study. Our main objective was to use habitat suitability modeling to describe potential distributional limitations of the Tennessee Heelsplitter. And really, too, what we were interested in was seeing, can we use readily available occurrence data and readily available environmental data to use habitat suitability modeling as an exploratory tool to help narrow our search scope for future research. So really help with making more efficient our planning for searching for more populations. And so we were hoping that we could highlight areas likely to harbor unknown populations of the Tennessee Heelsplitter throughout its historical range. To do this, we used maximum entropy modeling, or MaxEnt. This is a presence background algorithm, and while there are certain drawbacks to presence-only modeling, due to the exploratory nature of our objectives and also just a general lack of information regarding detectability of the Tennessee Heelsplitter, we found MaxEnt to be an attractive method for this specific study. So for our presence records for our model, we compiled records from agency databases, so qualitative field surveys, also museum records and heritage databases. We really were trying to just gather as much data as we possibly could. And we gathered about 350 occurrence records. And so after we removed, potentially erroneous records, also records that didn't have detailed locality information, we had about 200 records. However, we did also spatially thin the data to reduce spatial autocorrelation. And so after we did all of that, we had 119 presence records to use in our model. For environmental variables, I mentioned we were interested in variables that have already been derived. And so we had several hydrologic variables from multiple sources. We also had a layer for stream gradient, and we also took advantage of the NRCS's huge Surgo soil database, and so we had several layers for that as well. And we did perform analysis of covariance too, in order to make sure we didn't have highly correlated variables included in the model. We wanted to restrict our spatial extent to where we thought the species could realistically disperse, and so this is one of the most important steps of creating a MaxEnt model, and so we did remove the lower portion of the Tennessee River drainage from our. And since MaxEnt is a presence background algorithm, we of course didn't want our background points that MaxEnt randomly selected to come from the terrestrial portion of the landscape, and so we did clip our environmental variables to the NHD flow line in order to get around that. And so we also removed stream orders above 6 because the species is not known to have historically occurred in streams larger than that. And of course, we converted all of our environmental variables to the correct format of the same spatial resolution of 30 meters. For run type, we selected a bootstrapping resampling method. So we had MaxEnt use 75% of our presence data for training of our model, and then set aside 25% for model testing. For output, we chose the logistic output, so this gives you a map of your study area, and it assigns each grid cell a value from 0 to 1 of increasing habitat suitability, because we did want to see what areas our model was falling out as most suitable for the species. However, we also wanted to create a binary map of suitable and unsuitable habitat so that we could give that to our funding agencies. And so we chose the equal test sensitivity and specificity logistic threshold to do this. And to assess variable importance, there's several ways that Maxent outputs information for you to assess variable importance. And so we selected jackknife analysis to do this. And for model performance, we use the area under the receiver operating curve, or AUC. This is the most common model performance metric used in the literature for Maxent modeling. And it's generally accepted that any value of an AUC above 0.09 is considered good model performance. And I will note here that we know AUC can mean lots of different things, but with Maxent, AUC is defined as the probability that a randomly selected presence point will have a higher suitability score than a randomly selected background point. Getting into our results, our test AUC was 0.93, so that's above that threshold that I mentioned. So it appears we did have good model performance, and then our threshold that I mentioned was 0.15. And just so you can see our logistic output here, this is the northeast portion of our study area, and so you can see the areas that are red, orange, and green. One way to think about it is those areas are more environmentally similar based on the environmental variables we used to the presence points, so where we know the species can occur, than these darker blue areas that have a lower suitability score. So getting into the importance of the variables that we selected. So this is the jackknife analysis, so we can see how our different variables impacted our model performance. On the one hand, on their own, so these dark blue lines show you what happens to our test AUC when we only consider that variable. And so here we have mean annual flow stands out, as well as stream order, pH of the surrounding soil, and stream gradient. However, we can also use this jackknife to look at what happens to our model performance when we take out a variable. So we can see here when we remove flow, we do lose some model performance. And as well, groundwater table depth isn't particularly influential on its own. However, when we remove it, we do lose some model performance. And so this can help us see which variables might have environmental data contained in them that's not represented in any of our other variables. So I want to discuss some of these variables individually. So clearly mean annual flow was the most influential variable here. And so this is a response curve. This is just directly output from Maxent. And this shows how our different predictor variables impact our suitability scores. And so while our model doesn't really assess causal relationships, of course, between our species and our species presence and the variables that we selected, we can still think about what these patterns and suitability scores can mean ecologically. And so this black horizontal line is the threshold that I mentioned. And so according to our model and the threshold that we selected, anything below this line is unsuitable and anything above this line is suitable. And so clearly areas of low flow are best according to our model. And so we can see the species really seems to like, areas of low flow, and anything above, about 2,000 cubic feet per second is no longer considered suitable. And this makes sense with what we see in the field. This is a species that we often collect in, areas of really low current. And so we expected to see this, and it's what we observed. It's also not surprising that flow would be the most influential variable in our model just in general, because we know that flow can be an important driver of freshwater mussel presence and persistence. Stream gradient was also influential, so I wanted to touch on that briefly. We can see here pretty similar shape to our flow response curve, so suitably increased as stream gradient increased from about 0 to 50 decimeters per kilometer, and then we had a pretty drastic decline, and in areas above about 200 decimeters per kilometer were no longer suitable. So this is intuitive. Areas of high gradient probably have high water velocities, maybe scouring flows. It's really not a good recipe for a species like the Tennessee Heelsplitter. I want to discuss groundwater table depth. So we were interested in including some type of metric of spring potential, because several malacologists have noticed that the species seems to, occur in these areas. And so our thinking was that areas of shallow groundwater table depth might have higher spring potential and would therefore, be more suitable for the species and have higher suitability scores. However, that's not clearly from the response curve. That's not what we observed. So, we definitely don't want to say that springs are not important for the species. We still definitely do think that that's true. However, groundwater table depth was clearly not the best way to go about assessing this. And so we're hoping that as our knowledge of spring, habitat and presence improves, and that we can improve our capacity to model that relationship. Also, soil pH was influential. We didn't have access, unfortunately, to large-scale water pH data across the species range, and so we had to settle for soil pH. However, we know that the surrounding soil pH can affect adjacent streams, and so we saw that acidic pHs, low pHs were not suitable for the species, and suitability increased as pH became more neutral, and then as it became, a little bit too high, we started to have a decline in suitability. And so this is exactly what we expected. We know that mussels are not tolerant of acidic pHs, so that's a pattern that we expected to see in our model, and it's what we observed here. So just to wrap up in a brief conclusion, our model did sufficiently describe potential distributional limitations of our species based on the presence records we put into it and the variables that we selected to model. And so we think that this type of habitat suitability modeling can be a useful exploratory tool to use in accordance with your expert opinion to help narrow the search scope of future field surveys and make that planning more efficient. And we also think it can be useful in highlighting variables that might be good to consider for future hypothesis testing. All of these things are going to improve our understanding of the species habitat needs. And of course, future validation, field validation of this model will, of course, help assess the usefulness of the model, and we're hoping to do that later this year. And so and I just want to thank the U.S. Fish and Wildlife Service for the funding and Andrew Henderson for being a good partner with us working on this project, and of course anyone that gave me assistance and also anyone that gave me data, so records. This couldn't have been done without any of you, so I appreciate that. And with that, I hope to see y'all in the chat and can answer any questions that you might have.